curved the graph is, it eventually looks straight. That's the idea behind local linearity. Why is that important? Well, that means it's differentiable, and that means we can use a tangent line to approximate it locally. So right now we're just talking in 2D, just to kind of orient ourselves to what we're going to be talking about. So this would be the function of the square root of x plus 1 along with its tangent line at 0, right? We can see, okay, a lot of overlap here, but they basically diverge as we go to the left and to the right. Well, as we zoom in, this is what local linearity says. Any curved graph will eventually become straight, which allows it to be different, which means it is differentiable. And as we zoom in, we can see that they actually become the same. Hence the term local linearity. Locally, it's linear. Locally, we can approximate it with a tangent line. So I like starting in this because you guys have done tangent lines before. You did them in Calc 1. You did them in Calc 2 when you were doing Taylor polynomials, because a tangent line is just a Taylor polynomial of degree 1. So there's a couple things I want to point out about the tangent line before we generalize into 3D. So basically what's happening is we're at some point, and then the derivative gives us our rate of change. And then we look at the expected change in our output for any possible change in input. So let's say we've got a tangent line at 3. Okay, there's two pieces that are going on here. So what we've done is two basic things. We've made sure that we've matched the function value at 3. Interesting. And we've made sure we match the derivative at 3. That's what gives it that same shape as the graph. Now, one of the things I want to point out to you, I don't know if I'll be able to get this to annotate or not, but try one more time. One of the things I want to make sure we point out right here, this f prime of 3 times x minus 3, that's the differential. All right, so you watched the video today on the differential. The tangent line and the differential are very, very similar. In fact, the differential is part of the tangent line. What we'll see in 3D, the differential is actually just part of the tangent plane. What you want to think about when you think about differentials, what they're doing is they're approximating the amount of change for a change in input. So we have our general tangent line or first degree Taylor polynomial. Now, again, this is back in 2D. So in 3D, well, we know what a linear function looks like, right? So a tangent plane in 3D would be where we're going to match the function value, the partial with respect to x, and the partial with respect to y. So what that does is that gives us a local approximation of our surface. So if we bring up a function in our calcplot 3D, one of the things we can do, we put on a point here, so you can see my little blue point going along. I can have calcplot 3D add a tangent plane for me. All right, so you can see the tangent plane right here at that point. It's okay that the tangent plane goes through the curve. It just needs to be tangent at that point. And I can move it around and it'll basically move that tangent plane around. Kind of like we were talking about last time, if we get up here at the very peak, we get the spot where we get that horizontal tangent line because both our partials would be 0. But that's what a tangent plane looks like. Basically, it's the same concept as a tangent line expanded into 3D. And that just means we have to account for both the partial with respect to x and the partial with respect to y, which we can see is accounted for right in this equation. Finding it is actually not that difficult, and we'll do one a little bit later together, and then you guys will do one on the worksheet. But all you need is the function at AB, the partial with respect to x at AB, the partial with respect to y at AB, and then the point AB. So the only difference between this and Calc 1 is that you have to do both partials as opposed to just a single derivative. But now that we know how to do partials, this is something that we can do. So I like giving this image because it does a couple things. Number one, it shows a tangent plane right here at the point AB. So this is our point of tangency right there. And you can see this is our surface here. It's some curved surface. So our tangent plane is going to diverge from it a little bit. Okay, well, that makes sense. Now, here's the other reason I like to bring this up. This here, this is the expected change in z value given our partials, but you can see the actual change would be up here. So we're off by quite a bit. But what this is, notice f sub x delta x plus f sub y delta y, that's the differential. In fact, all we have to do is add f of AB to this differential, and we have our tangent plane. So the differential accounts for the change. You add the point that you add the point that you were looking for the tangent plane at, and that's what makes it the tangent plane. So they're not two separate topics. So right here, this part here without the f of AB, that's the differential, because what that does is it approximates the change in function value. Adding this on makes it a tangent plane. It's a plane that can be plotted by itself. That's what makes it have the same function value. And you guys are going to do one in the worksheet that's going to kind of bring this idea home of looking at change. Okay, let's talk a little bit about differentials. So in 2D, so again, we're back to 2D. Remember what I said, the differential is basically the derivative times the change in x. So I want to talk about this. So let's talk about square root of 9.2. I'm not able to annotate on here, so I'm just going to have to go to the board. But I want to talk about the difference between what the tangent line and the differential in 2D. It's the same idea in 3D. All right, so in this case, we're looking at a function. We'll call it square root of x, because we're going to be putting in 9.2. This is how these things work. Well, we locate the derivative first. So this is 1/2 x to the minus 1/2. And what we'll do, instead of evaluating these at 9.2, we're going to evaluate them at 9, because 9 is a perfect square. So we'll do f of 9, which is square root of 9, which is 3. And we'll do f prime of 9, which is 9 to the negative 1/2. That's 1 over the square root of 9, which is 1/3 times 1/2. 1/6. All right. Now, if we were setting up a tangent line, what we would do is we would say, okay, y is approximately f of 9 plus f prime of 9 times x minus 9. Okay. And so now if we wanted to get what square root of 9.2 is, we put 9.2 in for x. All right, well, let's do that. So we've got 3 plus 1/6, and we're doing 9.2, so 9.2 minus 9. So 3 plus 1/6. This leaves us with 0.2, which is 1/5. So I'm just going to keep the whole thing in fractions. And this thing comes out to be 3 1/30. So it's an approximation for the square root of 9.2. All right. Now, this we did with a tangent line. Okay. Here's the way a differential works. So the differential is specifically this part here. That's the differential. So the differential talks about how much we change by. So the differential says, well, hey, if I increase my input from 9 to 9.2, then I'd expect my output to go up by about 1/30. That's what the differential says. It looks at the change in output only. Whereas the tangent plane says the output is 3 1/30. The differential says our output that was 3 went up by 1/30. So they're very, very closely related. So I don't want you to think of them as two separate topics. All right. So the differential talks about our expected change in output. So differentials in 3 space, not complicated actually. It's f sub x times our change in x plus f sub y times our change in y. And shorthand notation, f sub x dx, f sub y dy. All right, so going back to my 2D example, that 1/5, that was our change in x. That would be what we're calling dx. Okay. We can call it delta x too. The reason we're using dx is because we're talking about what happens as these things get infinitely small. All right. So the important takeaway here is with differentials is that A, they're part of the tangent plane. They make up most of the tangent plane. The only thing is we need that anchor point to make it a tangent plane. The other thing that I want you to take away is differentials give an approximate change in output given changes in input. All right. So given a change in our x and our y, we can use the differential to approximate the change in our output. So why would we do that? Well, it gives us a way of measuring our expected change in output, in particular in situations where the functions may not be easy to work with, or we may not be able to work with the functions. Same reason we would use a tangent line approximation. It might be easier to work with than the actual function. Same reason we would use Taylor polynomials, because they might be easier to work with than the actual function and manipulate. Now, just like we learned in Calc 1, the smaller the dx, delta x, the smaller the delta y, the more accurate our approximation will be. We kind of saw that in the picture, right? You know, the closer we are to AB, well, the less error we're going to have. The further out we get, the more error that's possible. Doesn't mean it absolutely could happen. You know, this surface could have curved back down and just happened to hit at this point. But there's a reason that they're called local. Locally, they're good approximations. Globally, they're usually not. So that was our introduction into tangent planes and differentials. Again, Do not think of them as separate concepts. The differential is just part of the tangent plane. It's the part of the change. Any questions about tangent planes or differentials? You guys did great finding partials last time. If you can find partial derivatives, you can do tangent planes and you can do differentials.